Hey, rise and shine. Good morning, everybody. Thanks for coming out because this is a really fun kind of demo-focused talk because Bootable Containers is a open source project that Red Hat and a couple other organizations have contributed to in the cloud native space, but it kind of flips the deployment process on its head because typically for application developers they're trying to build for a certain target operating system like maybe CentOS or RHEL or another distribution, right? Instead of that, what Bootable Containers tries to do is essentially build an operating system as a container file. So use the same CI, CD, and cloud native container build process where you build, run, test, and run a container and do the same thing for operating systems. So it's a very interesting technology, and we're excited to show you how it powers things like operating systems such as Fedora Silverblue. Has anyone heard of this before? Okay, sweet. My guys over here, yeah. Or, I mean, everyone's used a Chromebook probably in their life, maybe. Our school bought like 5,000 of them, so we had to use them. And so this is the technology that powers immutable operating systems like this, because essentially you have the base operating system, some extra utilities. Like for us, we're going to show an AI application on top of the operating system, but it's built all at one time, so you don't worry about configuration drift or managing a fleet because you have this standardized build process that uses the same cloud native process you've been using for containers, but flips it for operating systems. So, my name is Cedric. I'm an open source engineer. I used to work on the Podman team. Anyone here use Podman? Yay, woo, we love Podman.
Me too.
Too, yeah. And then I'm also joined here by Paulo.
Hi, I'm Paulo. I'm senior architect in Red Hat, and my main focus is app dev, application modernization, DevOps, GitOps, and MLOps.
Yeah.
And really happy to have you and share the stage with Cedric.
Yeah, it's going to be fun. And you guys, are you raise your hand if you're a developer. Okay, awesome. And raise your other hand if you are a sysadmin, operations, anything like that. Okay, cool. Some of you guys do both, respect. But yeah, let's go ahead and kick it off. Now, I mentioned that it's Red Hat and a couple other organizations that are contributing this Bootable Containers project to the CNCF. It's also called image mode, if you might have heard of that. But this was kind of big news because this allows you to take, instead of just an application container with a base image and apps on top of it that use the underlying kernel, to actually add this kernel into this kind of unit. And from this unit, which is still a container image, we can build qcow2, an ISO, .raw, all these different types to manage VMs on cloud, on-premise, IoT, wherever your workloads actually live. Now, what's really cool is the same kind of CI/CD and process of packaging, building, and running and testing those applications for containers can also work for the operating system. Of course, Borat says, very nice. And that's why Podman is involved, because you need a container engine to be able to do that.
And it was super cool that Red Hat could give this products to the CNCF.
Right. Exactly, because it's going to be in kind of this neutral governance organization until perpetuity. That's a big word. All right. So if you're interested in the slides, feel free to check them out here. But this will give you a little bit of information about what bootable containers are and how to manage them. So how to build these operating systems. Today's demo, we're going to be working with CentOS Stream, and we're going to be adding a couple different containerized applications on top. But what's really cool is we're using OS Tree and a couple other utilities to kind of build this into the operating system itself, right? And so what's really cool is, you can maybe read and write to a couple directories, but other than that, the image is immutable. So let's say, as a sysadmin, you're maybe working with CVEs and making sure everything's up to date. What's really cool is you kind of define this in one container file using some type of base image that's already been compiled for you, so it's up to date, and then you deliver it to everything, instead of patching certain machines as you go and working with, configuration drift as well. So that kind of, before we talk about that, I just also want to mention a show that we work on. So Red Hat Dan on Tech is Daniel Walsh, and he's kind of the founder of SE Linux and a couple other Linux utilities Feel free to check this out. We interview lots of people working on open source projects, from systemd to Podman, the container project, and much more. So, Paulo, what are bootable containers and what do they solve?
I'm glad you asked, Cedric, because we keep talking here about bootable container, but what exactly is a bootable container? What is the problem we try to solve here? And when we build any type of tools, any techs, is normally to solve some common problem, some common challenge. So you have like a different teams and different systems that you need to deploy this platform, and then you go there. Normally you have like a customization of your operation system, of your containers to different deployments on different platforms, and then you see like different teams working, automating this with probably like with Ansible or some automation tools. And another team, you could be surprised, that might be like doing everything by hand and changing those customized files, right? And that's make it very difficult to maintain and upgrade. And there's all these upgradations and things is not really in some of the times not countable on the budget, and you need to negotiate on the open windows of your new releases to deploy this. Like say, for example, you have heard of a new patch security on new release base image, and you're still running a 2 years old base image, and you need to upgrade all these container images, and become really difficult. So we still have like some challenge involved with the operation system on the size of the containers itself. And we all heard and know about the immutable containers way. So you can't really go there and mess around with containers. So it's all written in stone. You build it, you push it and deploy it, and you're not going to allow any people like to change anything, even operation system related things. And that's where bootable containers can come in handy and help with their problems. And then before we just jump in bootable containers and explain, let's just go a little bit a step back and do a recap of how a container works. And I hope everybody is already familiar with containers, but let's just explain what the container come in place in first place, right? So we have like an application in your base image and operation system all compiled there, and it was very difficult back then on the time to actually deploy things in production. And it was normally would be like building and coding in one operation system, and the production server is a different operation system version, or even is the same, but you have like a variation things in production, like you're missing event variables or system configuration or file paths or class paths there that really didn't match with what was working there. So the container came to isolate this thing and solve that problem, like works in my machine, but doesn't work in production. So I come from a long background of application developing Java from even early days before Java frameworks, you guys probably familiar, was existing. So I work with Java 1.4 and start to like see all this evolution to a container and all this pain that we have before. So now we can like move this container throughout different environments when it's ready, and not going to be different with bootable container as well. So in a traditional container, you have, so what is the difference then, right? So the bootable containers, you have the application, the operation system, and your base image on a traditional way. And typically, you have your kernel outside of that with your drives and your configuration for your infrastructure outside of containers. So what we're doing here is moving the Linux kernel inside of the container. And so let's answer the question right now. Like, what is the bootable container then? So we have the OCI container, so the Open Container Initiative. So you're still building if your recipe or if your Containerfile or your Docker file, and you're still using your native toolings to automate your installation, your best practice to containerize your application container. But we're putting the entire OS plus the kernel there. So let's make more like automated and in a more easy, manageable way to configure all this infrastructure that you have inside of the container. Right, so let's have a look now on how this deploy and the update system works. So like I said, you have your Docker file, your container files that you build in a prescription way. Then you do the building of your container image, also like your CI/CD pipelines in traditional way. But it's not just about like wrapping up your operation system inside of a container file. The great thing here with the bootable containers is create and convert to a disk image, and that can be deployed to different platforms like edge devices, public cloud, virtualizations in bare metal. Let's say, like for example, you have like your Quarkus Java or Python application running on a container, in a bootable container that needs a control of your system, your operation system there, and then you deploy in a podman and a bare metal and create like a cluster with RHEL and put it all in high availability. Or you need to deploy that in edge devices, and then when you need to update, you do the same way you do, like you bake your image, you push the container registry, you just can pull down from there and update those containers. And then you have the core thing that runs on the container, which is the bootc CLI tool. And if you can tell us more about that, Cedric.
Yeah, because it's really interesting because say you're on maybe, let's say, for example, RHEL, and you've got that as the base image, and you're on 9.6, right? You can use bootc to swap or switch to a future upgrade like a 9.7 without having to kind of kill the machine, delete the machine. It's essentially you're just going to swap out all of the base files and kind of the root directory to do this upgrade, which is really interesting. So you can use this not only for like the base operating system, but you can also do this for the application workload. And so it's kind of just a CLI utility that'll allow you to make these upgrades. You can either do it on like a cron job, or you can do it at any given time where it'll just download the new layers that you need for your workload from the registry that you have, and then on update, it'll boot into that. Because say, for example, you have an IoT device where you're limited connection, you might have internet 30% of the time. Well, you can just download those layers then, and then on the next reboot, upgrade to the next version of the workload or the operating system. So it's a very cool way to manage these bootable containers. So these are some of the commands to upgrade. You can stage this, and then you can roll back. Say, for example, if you have a boot failure, you would just roll back into a previous version, working version of the operating system as well. So it's it's a pretty cool utility.
Yeah. And we're going to see some of that today, right?
Yes, yeah, we'll check it out.
Cool. And that's come more hand on my side of my expertise, because I help customers doing app modernization, so we need to containerize applications. Then that's the way as a Containerfile, if you're not familiar. So we're not going to change much. So we're going to do a from, where you specify where your base image comes from. And this base image we're going to use is the CentOS bootc base image. So we come with the CLI command tools already installed on that. Can you also customize that image and create your own customized image? Then you do your run for DNF install. Then you can install your package, your Python version or your JDK version, whatever you need to put there inside. And then you do your copy for your unpacked application files. Then you copy all your configuration files, and you run all your script, automation script. Then you put that in a container file or a doc file, and you run your bake build, and you push your registry, your image. And the benefit, the beautiful of all the open source toolings, you have the repo there that you can check for yourself, go there, contribute, see the things that we have been doing and work there together. And like I said, you can customize your base image, but Red Hat also provides some base image already for you. So we have Fedora base image, and we have CentOS stream base image, so we can use those base image already. But if you want more like a security stable enterprise version of that base image, you go through a Red Hat Enterprise Linux to do that. So that's the URL with the list of base image containers we have. So
yeah, and in the slides, feel free to check them out. Well, we're not a bot, don't worry. You can see some of these base images. So here we have CentOS Stream 9. So if we come over to this GitLab instance for CentOS Stream 9, you can see all of kind of the source for this base image in the container file. So this is what's building that source base image, and you can see some of these different tools in order to, like rootfs, generate the roots file system for this bootable container. So it's really cool way to kind of see what's happening underneath the hood because all of this with bootable containers is open source. So yeah, more information there if you're interested.
Cool.
And then to make this all happen, you could use Podman or your favorite container engine. And today we're going to be using Podman Desktop, which is a visual GUI for Podman that has an extension specifically for bootable containers. So it allows you to specifically generate your disk type. So we'll check out what this kind of looks like here in a second. But it also allows you to run these virtual machines in order to test things before you actually deploy it to maybe a cloud environment or something like that. And there's some examples as well. So open source project, it's made for containers and Kubernetes, but this is an extension to allow you to build these disk images from your container images that are bootc enabled. So we'll kind of check this out. And before we do that, we also want to plug image mode because there's a workshop online that will allow you to test out bootable containers yourself in this kind of isolated environment. And this is with RHEL. So you'll see today, and this is the upstream open source version. There's also the RHEL version for folks that need all of those kind of governance, security, and additional kind of checks when they're building these applications as well.
I just want to add this, like, if you start thinking, you guys gonna start building bootable containers and replace all the old type of containers, that's not the aim for this. Is bootable containers is for a specifically system control that you need those containers, and traditional containers gonna live together with them. And we're gonna see the bootable container powerful things today, and we're very excited about it because if you need, even with the AI things that are coming now along, you can use your bootable container to configure your GPU drivers and then use the command line to change GPU drivers and on the go.
Yeah, exactly. Because that's, I'll say, is I've been doing some AI work very tricky. Because some of the bootable container use cases that we've taken a look at is for AI applications. Our customers are asking for AI agent or like a RAG chatbot with PDFs, and I need to be using this specific version of transformers, and I need to be using this specific dependency and a specific kernel, and it's very, very complicated because when one thing goes out of whack, everything else breaks. And so that's what my team has been using them for, but there's also edge appliances as a great use case to be able to package everything up and deploy that to IoT devices, and just being able to do one app to one host.
Especially on these network environments that you have everything discontinued, or the edge devices like Cedric was explaining, that you can lose the connection of the network, but with bootable containers you can streamline this and recover it to the latest operation system, and then you can update when the connection gets back.
Right, exactly. We'll take a quick look for the demo today at AI stacks, because as I mentioned before, on top of the kernel and any acceleration, you've got the drivers and frameworks that you'll need in order to do accelerated compute. You'll need frameworks or whatever type of model serving engine, and then a model on top. And this can be very complicated if you're trying to maintain this in multiple environments, just because some transformer upgrade might be needed, or you're probably swapping out models quite frequently. And so to be able to do this all within our standardized, cloud native pipeline, where we're building from a container file and pushing that to a registry, is much easier than manually going into these machines or having to do upgrades and automate this as well. So this is the stack we'll be taking a look at today. It's a big opportunity just because we have been using this ourselves for the AI inference server for RHEL. So if you've heard of this before, it's just a VLLM, which is a enterprise AI runtime that allows you to run open source models like Qwen or DeepSeek or something like that. But by assembling all of this at build time versus production, you've got a lot of stability in the way that we roll out these releases, because people at the end of the day, they just want it to work, right? And if we're having to kind of debug things and kind of fix these compiler errors and kind of go back and forth, we're wasting a lot of time that could be used in other areas. So it's a big opportunity.
True, and we've been using that with our customers and having really good feedback.
Yep, exactly. Well, Paulo, I want to build my own bootable container. let's take a look at how that
Yeah,
works with the extension.
let's have a look how that's actually work, that powerful things on the bootable container.
Yeah, let's do it. So that extension lets you go from the container image to whatever kind of disk type you want, and we'll show how that works. We've got a live demo, but I'm just kind of walking through really quickly. So you work from the Containerfile, which has that boot C enabled base image. You select which platform you want it to work on. From there, you can test things out. But then if you want to build it for a disk image, you then select that base image, output wherever you want it to go, and then build for that disk type. And then you can run it as a VM. You can deploy it wherever you need, and then launch it in a VM to make sure that everything is working. And that's where the boot C utility to upgrade or swap from different versions of the OS or of the application comes into play. So, are we ready for a little demo?
Woo! Woo, yeah.
Cool.
It was not easy to get that to work right this morning, right? So
it's been
we
tricky.
hope you guys enjoy.
It's been tricky. So as I mentioned, we'll work with the AI application. It's just going to be a code generation because who's using like Claude Code or something like that? Okay, yeah. My vibe coders or spec coders or I don't even know what it's called anymore. AI engineering, I guess.
Yeah.
And so we're going to test out first the build stage of this kind of process of deploying out a workload, right? So model discovery, developing locally, and I guess also creating a container image. And so this kind of build phase is what we want to focus on first. So this is the open source Podman desktop, and it originally is focused for containers. So you can see I've got tons of different Redis cache, et cetera, that are all running locally. And the way we'll actually run this is through a pod. So you don't have to know too much about it, but it's just going to allow us to group multiple containers together in one environment. Now, the extensions allow us to download the bootable container extension here, which is, it's funny because it's actually an OCI image itself that's also running on Podman desktop, so it's like very meta, Inception type.
Yeah. These containers running containers.
Exactly, containers running containers. And so I've already installed it here, and you can see that there's kind of some examples of common use cases that you would want to build with bootable container that are kind of just generic. So one that can connect to Wi-Fi, one with Tailscale, one that's just a container being managed by systemd. So that's quite interesting use case for this kind of one-to-one application to host situation, and Apache and several others. But what I want to do is show you the application first. So let me come over here, and the app is quite simple, one file that is essentially using LangChain to connect to a model server that's running locally. So it's connecting to the V1 OpenAI API, so we don't have to switch anything. And first, we'll check for model service, just to make sure everything is running. We're using Streamlit to do the UI. You'll see this here in a second for code generation app. And then we're using this OpenAI API to say, hey, you're a helpful code assistant. You answer the user's question. And then we kind of just have this logic here in order to talk from the user to the actual model itself. Now, the container file here is our standard application container file. So we've got Python as a UBI, or universal base image, based on RHEL. Anyone can use this to build their container images with, because it's specific for Python or Java developers or Node.js. We're copying in the requirements, the source files, and then we're just saying, hey, Streamlit, run this Python application. All right, so let's go ahead and check that out. I'm going to come over here. This is another extension that will just allow me to run it with one click. So let me delete this. I had to make sure it worked earlier. And we'll just start it up. No,
it's all live.
It's all live. That's what we want to make sure.
Recorded.
Yeah. So let me come over here. Here you can see we can kind of pick the model. So you don't have to worry too much about this. But you'll notice a couple steps here where we've got the model that we're going to load in, an inference server, and that code gen application that we just saw. So this is our application workload running in a container. Here you can see, bam, we've got that kind of UI here from Streamlit. And then we're going to, in the background, make a call to the model. So I'll just show you the logs here of our pod. Started 18 seconds ago. And we'll say, Oh, what's an obscure programming language that someone wants to see? Like Pascal. Okay,
Pascal.
that works with me. Right. Hello world in Pascal. And trust me, I've never seen Pascal. So, okay. Yeah.
Guys,
In COBOL?
the one in Lua, because
Oh,
I'm biased with Lua, so
world in LUA, right?
Lua, yeah.
Okay, so it's pretty basic model. It's Mistral, so one of the French models here.
Yeah.
And we've got our application running here pretty easily. We can kind of see it. Check the model. We got the responses back quite fast. And if we want to make changes from this point on, right, we're just going to say this is the DevOps code generation app, right? And we rebuild everything from over here. So restart this app with the current changes that we have. And this is our typical container workflow, right? So let's refresh here. Oh, it's probably restarting everything. There we go. This is our container workflow, right? So we're just making changes on the fly. And this is quite easy for us as application developers. But the next stage is how do we convert this to an operating system? And typically, right, we would be building this, pushing it to a registry, and then pulling it down on our host and hoping that everything works and that things are up to date and patched, and we're going to be able to talk to the other applications.
Exactly.
Right? So we're kind of like, I hope it works. So being able to put this in a bootable container makes a huge difference because we can have this ability to quickly edit and modify the disk image itself without having to go in there, do SSH or whatever it needs to be, or Ansible. We're just doing it completely from a container file itself. So in the same repository, and we'll have the source code for this also in the slides, but you can see there's a boot C folder. And this is our bootable containers container file. So it's starting from that stream9 base image, which includes the kernel. And we're doing a few steps here. So we're adding an SSH key just to be able to get in there from our local directory. And we have a few arguments. So code generation is just the specific kind of tag we want to give it. And we're pulling in a few things. So we're pulling in Mistral's coding model. And we're also pulling in a specific app image. So the app image is the one that we just built. If I come over here and I just add code gen, you'll see that someone has already built and pushed this to a registry. So you could imagine this is our team working on the application. And so we might have V1, V2. And then finally, in addition to the app and the model, we're going to have an inference server. Has anyone heard of Llama C++ before? Okay, sweet. If you've ever used something called ollama, this is the inference engine that runs underneath it. So I'll just kind of show you, quite popular, but it just allows you to run models on CPU instead of needing a GPU, which is really cool. So those are the three components that we're pulling in for the specific base image. And the thing is, to have them start on boot, we're going to be using systemd. So we're copying in this unit file from this build directory that's going to set things up on boot. So it's kind of, quite simple here, but it's just saying, hey, we have a few images, and they're wanted by a specific service that we're going to create. And then we're also going to be using, oh, here we go, yeah, sorry. We're also going to be pointing to a codegen.yaml, which is going to, with Podman, define the relationship between the containers. So here we go. It's kind of just a Kubernetes YAML here, but it's just saying, hey, we have containers to start on initialize, so the coding model. As an endpoint, we're pointing to everything as it should be with the container image itself. And then we've got the Python inference server, and then pointing to where the model is going to live. So this is all going to be copied in to the operating system at boot, and we're going to be using these combination of unit files in order to set things up and ensure that when the system boots, all of these containers are ready to go. All right, so we can come back over to the container file here. And here you can also see that we've got a Podman pull just in case we don't already have them. And it's using Quadlet in order to do this systemd management. So if you're interested in just without bootable containers, how you manage systemd working with containers on boot or anything like that, check out Quadlet It's a really cool project, part of Podman as well. But that's really all it is. And so we'll kind of go ahead and kick this off here. So I've kind of ran this already before because the internet, you never know. But we're using a makefile to just copy in all this configuration. We're going to tag it as my specific registry and kick this off. So you'll see all of these steps happening. So first off is copying in the SSH up here. And then we're going to add in these arguments, copy in those configuration files for boot, and then the Podman pool for the specific server app and model, and tag this. And so now we've got this boot C enabled base image. And what this looks like in something like Podman Desktop is when we search, you've got a couple here, but specifically this one, now we can see it's a little bit bigger because we're also including the kernel itself underneath, but we can inspect, we can see the history and kind of the different layers of this. And so you can see we label this as CentOS stream. We have OS tree that is going to be building the base layer itself underneath. And we've got all of the modules and utilities to do these upgrades. So here we've got boot C as a utility, but we also have all the Linux firmware. We've got Podman. We've got configuration utilities. So everything that we would need to build this into a operating system, we've got now in this base image. And when we want to do upgrades, we've got this Containerfile to start as a source of truth. So
cool.
Yeah. Building this into an actual operating system itself. So we've got the bootable containers dashboard. And here you can see any of those boot C enabled base images now populate inside of this extension. And the step in order to get this into a VM or something like that is to come over here to these available container images with boot C and select what type of disk image that we want this to go to. So there's a utility called the boot C image builder, which is made for converting this into exactly what we need, like .iso or .qcow or Amazon disk image for a specific file system. So I'll just set default. And if there's any other configuration that you need, such as users or a public key for SSH or file systems, anything else like that, you can add that in here. We're not going to touch this here just because we're going to run everything locally. But maybe you also want to upload this to a cloud or something like that. You can just specify the bucket and then build that in the cloud as well. So let's come back over here. We can select multiple, but I was having a little bit of trouble building one of these specific base images. So we've got kind of this example here of just the Stream 9 itself and how it goes from a container to that disk image. And so you actually see the command that is ran here that you could run yourself in the terminal right here. And as I mentioned, it's a Podman run, and we're using a specific image builder that you can find on GitHub or on the registry. And we're just giving all of the instructions for the source container image to be translated now into a qcow too. And so we won't go into the logs too much here, but you can see the file system being built out. And at the end of the day, we've got this result saved after about 25 seconds. So it only took about half a minute in order to take this base image into an actual file system to be deployed. And so I'll kind of show you what this looks like. Here is for getting this from the base image container to an actual file system. Now we have all of the components here that we need in order to, about a gigabyte and a half, to go from the image itself, right, to the components needed to deploy this workload in a virtual machine or anything like that. And so we can kind of take this, and I'll show you here, go to maybe something like a qcow. So take this qcow or like a .raw, start this, and you'll see this progressing here. Oops, let me come back. Oh, hold on, sorry. You can see the build log as this is going. And yeah, if you want to run this yourself in the terminal, you can. But that's kind of the process of going through this, where in the previous kind of step, we were just building our actual application container. And then now it's, hey, how do we convert this to a disk image and deploy it either locally or remotely and manage this? Because all we have to do when there's an update to this operating system is now, hey, say that we have a different container image, say it's version 2 or something like that, then we would take this container file, we would go to build this again, right? Take that disk or take that image, push it to a registry, and then use the bootc utility in a virtual machine to do that. I had a little bit of trouble getting the VM to work for this specific workload, but you can kind of create a VM here in order to run things using Macadam. Apologies for that, but we do have the lab online that you could try out to see the other side of the process. But this is kind of everything that the developer or the ops would do in order to get to that disk image. And with the disk image on boot, those containers would be pulled, started, and ran. And that's the beauty of bootable containers, is that we're doing everything from container files with our CI/CD process. Now, today we didn't do much, but you could imagine if you have this running in a production environment, you're setting up checks for who wrote to the code and any CVEs and et cetera, et cetera. So that's the beauty of bootable containers. I'll also provide here the repo for what we were doing today. If you're looking to get into the code, you can try this out yourself. The slides are there again. But on behalf of me and Paulo, we really appreciate your time. Hopefully you found some cool new insight that you can now do with containers and make your life a little bit easier. So feel free to hang out here or come to the Red Hat booth, and we're happy to answer any questions. But enjoy the rest of the conference. And then in the Red Hat booth, you can get your ticket for night out today, and you're all invited to join us there. So we have a social, free beer, free drinks, not just beer, but free drinks, right? So you can all join there as well, and then we can talk more about it. Yeah. Thank you. Thank you very much, guys. Thank you, Cedric.